Hello everybody, welcome to this introductory course on cooperative game theory. In this course I will use basically two books. There is one book by Roger McCain called Game Theory, a Non-Technical Introduction to the Analysis of Strategies. And there's another book which is more in-depth by Roger B. Meyerson, Game Theory, Analysis of Conflicts, where we will find much more details than the first book, but of course it's also more advanced. In this first lecture we will deal with non-cooperative game theory as starting point. But first of all, of course, we have to clarify what is game theory about at all. Game theory is not about computer games. This is a common misunderstanding. But it's a mathematical discipline studying models of conflict and cooperation between rational, intelligent decision makers as an approach to model human behavior. You will have noticed in this definition the word rational decision makers. So what does rationality mean? Rationality basically stands for the idea that a player who is choosing a strategy is doing this in order to maximize his own individual reward. So it's a selfish behavior in a certain sense. So it is basically this principle of rationality which serves as the key link between neoclassical economics and game theory. But of course, the outcome of a game between players depends not only on the strategic choice of one player, but on the strategic choices of all the players. So it's the player who is choosing a strategy and the other players answering the strategy. This is the basic idea. If we would like to define this formally, a game consists basically of four ingredients. We have players, we have action sequences or moves, so the rules of the game. We have a space of potential strategies, of options for players to how they could behave. And we have finally a so-called payoff function which gives us the result, the outcome of the game. Four ingredients. And most important, we are dealing with strategies, and the strategy space, once again, is the set of player options in each phase of the game. There are various types of games, and I won't go into details here, but all of them have as a central solution concept the idea of going for an equilibrium. So what does equilibrium mean? This is a state of a game where none of the players has any incentive to change anymore the chosen strategy. And if you achieve such a state, then the game somehow comes to an end, it stops. And this gives us a good idea of what the result of a game could be. There are, of course, many different types of such equilibria. In a minute we will learn about the so-called dominant strategy equilibrium. A bit later we will talk about the Nash equilibrium. There are others like Maximin equilibrium, Wardrop equilibrium, the Shapley value, which we will deal way later with, and a couple of others as well. So, to dive straight into the topic, it's maybe a good idea to deal with the most famous game at all, the so-called prisoner's dilemma. So the story behind the prisoner's dilemma is as follows. There are two bank robbers, Al and Bob, who are robbing a bank. After finishing their job, they are unfortunately arrested by the police. However, the police doesn't have enough evidence to sentence both of them. So they start with interviewing the two robbers separately, in separate rooms. They have no possibility to communicate with each other. And the police offers them the following deal. If one of them testifies against the other and the other stays silent, the betrayer goes free. And the silent one receives the full 10-year sentence in prison. If both of them defect, both are arrested only 1 year for reckless driving, for instance, because evidence is not sufficient. But if each betrays the other one, both will receive a 2-year sentence. So we can summarize this deal in a matrix like the following, and this is typical for this type of games, that we derive a so-called payoff matrix describing the result of the game. So we have L on this side in blue and Bob on the top, and both of them have two options, two strategies. Bob can confess or stay silent, and L can confess or stay silent. And if we put now this story into numbers here, Then the numbers, of course, are non-positive because a sentence is something negative. So let's remember, if one testifies against the other and the other stays silent, the betrayer goes free, which means 0 years in prison, and the silent one receives 10 years sentence. So if Bob does not confess and L confesses, L gets free, 0 is the first number in these brackets, the blue one, and Bob gets 10 years of prison, minus 10. And for symmetry reason, the other way around as well. If Bob's confessing and L is not confessing, L will be sentenced 10 years and Bob goes free. If both of them confess, option 3, both of them will get minus 2. And if none of them confesses, both of them will get minus 1. So this payoff matrix precisely describes the outcome of the game. No, not yet the outcome. The story behind the game. And the question, of course, for the prisoners is which strategy should each of them choose. Remember, they cannot communicate with each other. This is the idea of non-cooperative games, no communication. So the question for us is a different one. In fact, there are 3 questions. So question 1, what makes one strategy better than the other strategy? What does better mean? Question 2, what makes an outcome better than another outcome? And question 3, how will most probably the outcome of this game, the outcome of this situation, will look like at all? So let's answer these 3 questions one after the other. Question 1, what is a good strategy? Well, a sufficient condition for a good strategy is for sure if this strategy is better than all other strategies independently of what the other player is doing. And we call such a strategy dominant. So here's the definition once more. A strategy is called dominant if, regardless of what the other players do, the strategy earns a player a larger payoff than any other. Depending on whether better is defined with weak or strict inequalities, the strategy is termed strictly dominant or weakly dominant. But this is a side remark. So what does this mean in the case of the prisoner's dilemma? Let's consider L, for instance. L is having 2 options, 2 strategies to confess or not to confess. And the question is one of these 2 strategies better than the other, independently of what Bob is doing? Let's have a look at that. If Bob is confessing, what should L do? Well, if Bob is confessing and L doesn't confess, L gets 10 years of prison, and if he confesses as well, he gets 2 years of prison. So for sure in this case, he should confess as well. If Bob is not confessing, then L again has 2 strategies. If he doesn't confess either, he gets minus 1 year in prison. If he confesses, he gets 0 years. So in both cases, confessing is for L a better idea. Independently of what Bob's doing, confessing is the dominant strategy for L. And of course, for symmetry reason, this is also true for Bob. So eventually, if they follow this idea, both of them will confess and both of them will go to prison for 2 years. Well, problem solved. We have a solution for our game, but apparently we are not really happy with that. Because there would be another solution where both of the players would be better off, but they didn't achieve this solution. They didn't come to this solution. And this brings us to the next question. When is a solution better than another one? What is a good outcome? And one definition for that is the so-called Pareto efficiency. It's termed after a scientist called Vilfredo Pareto. And the idea is an allocation of goods is called Pareto efficient if there is no other solution points for which all players are at least as well off and at least one player is better off, strictly better off. So this is a way to compare 2 potential solutions. One solution is better than the other if all players are not worse off there and one of them is better off. Of course, there are situations where one player is better off and the other one is worse off, then you cannot really compare them easily. But with this criterion of Pareto efficiency, you can make such a comparison. And it's pretty clear that if we compare these 2 solutions, the one where both of them do not confess makes both of them better off, and in this sense in this Pareto efficiency sense is of course a better solution than the one here. So if we apply this criterion, we would end up with the solution here. Both of them should not confess, which is the so-called social optimum. And this is also, of course, the dilemma. If they behave according to this dominant strategy idea, they will end up here. If they go for the social optimum, they will end up here. So now let's turn to question 3. What will be the probable outcome of the game? And we have already indicated in the introduction that a good solution concept is the concept of an equilibrium. If we now consider the situation where both players have such dominant strategies, it's pretty clear that if both of them choose this dominant strategy, they will end up in an equilibrium immediately. They have no incentive to change their behavior. But there is also a weaker version for this equilibrium idea, the so-called Nash equilibrium. So a Nash equilibrium is defined as follows. If there is a set of strategies with the property that no player can benefit by changing the strategy is chosen, while the other players keep their strategies unchanged, at least for the moment, and if this applies to all the players, then we have an equilibrium as well. And this set of strategies and the corresponding payoff is then called a Nash equilibrium. And it's pretty clear that any dominant strategy equilibrium is a Nash equilibrium, but we do not need anymore the concept of dominant strategies to end up in a situation where we have Nash equilibria. So this is a more general concept. You might wonder where the name Nash equilibrium comes from. In fact, this was a scientist called John Nash, and you know him maybe from this movie A Beautiful Mind, which was in the cinemas a couple of years ago. And John Nash, this is a picture from real life, in fact during his Nobel Laureate Award ceremony, was one of the most important groundbreakers in game theory, together with John von Neumann, whom you also might know as a computer scientist who has basically laid the groundwork for all this theory. So if we come back again to our prisoner's dilemma, it's clear that we will end up in a dominant strategy equilibrium here, and this is also a Nash equilibrium. Why is this the case? Well, we can answer this very easily if we go along all the potential solutions and see whether they can be Nash equilibria in the sense of this definition. So let's start down here. If both of them have chosen as their strategy not to confess, and if L now has the possibility to change the strategy, he has to wonder, should he change his strategy or not? While Bob is staying with his strategy for the moment. The other players keep their strategies unchanged. Bob is not changing his strategy at the moment. And of course L will decide to change his strategy because 0 is better than -1. So in this sense, this solution here is not a Nash equilibrium. Now we can ask, is this a Nash equilibrium? And now we have to change the roles. Now L is keeping his strategy unchanged, and Bob has the possibility to choose another strategy. So Bob is the red one, remember. Should Bob change his strategy? Well, if he stays with the current strategy, he gets 10 years. If he changes, he gets 2 years. Of course, he will change. So this is also not a Nash equilibrium. And now we are here. The question is this a Nash equilibrium? Again, we are reversing the roles. Bob is keeping his strategy unchanged. L is considering to change the strategy. Should he change? -2 versus -10? No, he shouldn't. Let's reverse again. L stays with the strategy. Should Bob change his strategy? Of course not, because he has changed it to confess as a reaction to L confessing. So we have now a stable solution. But this was not referring to the question of dominant strategies, but this was another more general approach. So, what's the dilemma of the prisoners? Well, we have already seen that obviously the social optimum achieved by both prisoners, the Pareto efficient optimum, is achieved if they are defecting. But individual optimization drives them to the Nash equilibrium, and both of them are not the same. The Nash equilibrium, in a sense, is worse for both of the players, and this is their dilemma. Now you may wonder whether this is a purely theoretical example because probably you have never robbed a bank yourself, maybe you even don't know a bank robber personally, but there are examples from real life where this immediately applies. And one of them is, for instance, the World Championship in soccer. In 2006 there was the final in Berlin, and there was a very, very famous scene where a guy called Zinedine Zidane was reacting to another guy called Materazzi, because he was insulted by Materazzi, and then he committed a very bad foul and he got the red card and was sent off the place. So let's try to model this situation. It's a simplified model because we do not consider that there has been an action and a reaction. We consider both of these actions taking place at the same time, a so-called one-shot game. So assume both of the players have a certain aggression level A, which is, for instance, between 0 and 5. 5 is very high aggression, 0 is no aggression. And let's consider their objective to minimize their individual aggression level. So, can we devise strategies and can we model this as a game? Here we have Marco Materazzi. Materazzi could have been staying silent, or he could insult Zinedine Zidane. And Zinedine Zidane could stay calm, or he could attack. Let's look at all these four combinations. If Materazzi is staying silent and Zidane is staying calm, both of them have, say, an average aggression level. They are in the midst of an important football, an important soccer game. So let's say they have both of them an aggression level of 2. And it's symmetric, of course. So if Materazzi would have been staying silent and Zidane attacks, then Materazzi would be very, very, very aggressive. This is pretty clear. So let's give him a 5 for this situation, and Zidane would get rid of all his aggression levels because he pushed out his energy, so 0. The other way around, if Materazzi is insulting, he would get out his aggression. And Zidane staying calm would be, you know, very aggressive, but he wouldn't have been doing anything. So this gives us a combination 0 for Materazzi and 5 for Zidane. And if both of them attack, in the case of Zidane, and insult, in the case of Materazzi, well, Zidane will increase his aggression level because he is sent off, he has to leave the game. And Materazzi increases his aggression level as well because he has been violated by Zidane. And he is now very angry as well, but not as angry as in the case of these 5. So let's say 3 for them, both of them. And if this is the payoff matrix of this game, it's pretty easy to see what happens. Let's again look at the two players. So Materazzi, should he stay silent or should he insult? Well, the first question is there a dominant strategy? So let's consider the case of Zidane staying calm. Then Materazzi, remember, in order to minimize his aggression, should insult him. While insulting, he has an aggression level of 0. If he stays silent, he has 2. If Zidane is attacking, Materazzi should also insult him. 3 is better than 5, minimizing the aggression level. So, clearly, insulting is a dominant strategy for Materazzi. What's the case for Zidane? Well, let's assume Materazzi is staying silent. So Zidane should, well, attack. Because in the case of an attack, he has an aggression level of 0. If not, if he's staying calm, he has 2. If Materazzi is insulting, Zidane should attack as well. 3 is less than 5. So also for Zidane, attacking is a dominant strategy. Both of them have dominant strategies, and inevitably they end up in the situation where both of them, the one is insulting, the other one is attacking. Even if staying silent would have been socially better for both of them. So this is a very clear explanation of this situation, which seemed to be quite strange at the time, but game theory is apparently able to provide a consistent explanation. This is nothing else than prisoner's dilemma reloaded. So the last question for today is, if there is a Nash equilibrium, and this is, remember, it's not clear, not every game has to have a Nash equilibrium, but if there is one, is this Nash equilibrium unique or not? Let's consider another example. There are 2 radio stations competing for their audience, and they have to decide which type of program to play. So they do a market study, and the market study reveals 50% of the audience are interested in pop music, 30% of the audience are interested in news, and 20% say are interested in classical music. Now the two stations have to decide which strategy to choose. And the problem is, if both of them go for the same type of program, they will just share their respective market segment 50-50. If not, they will get the whole market segment they are addressing. So what should they do? Again, we can model this with the help of such a payoff matrix. So we have radio A here, we have radio B here, and the situation is reflected in the fact that we have now 3 strategies for each of them. And as we said, if both of them go for the same strategy, they share this audience. So if both of them go for pop, 50% of the audience are interested in pop, so both of them will get 25% of the audience. So therefore 25-25 in this payoff matrix. If, for instance, radio A goes for pop music and radio B for classical music, pop music is 50%, classics is 20%, then we end up with a payoff of 50 for radio A and 20 for radio B. And in this way you can fill this matrix, and please do it for yourself, because then there are 2 questions. Is there a Nash equilibrium in this case? And if there is one, is there only one? Is it unique, or can we find another second Nash equilibrium? I leave this for you. As a final example for today, we will consider a game called Divide the Dollars. This is a very interesting game, and it will serve us as a guideline also for later lectures. The game goes as follows. You have 2 players, and there are $100 on the table. Well, I don't have $100, so let's say it's 10 euros. Put them on the table. And now the players are asked individually to propose how to split this amount of money. If both of them propose the same distribution, the same split, they get what they have proposed. However, if their proposals disagree, neither of them gets anything. And the question is there a Nash equilibrium? Is there more than one Nash equilibrium in this case? And if so, how many can you identify? And I suggest, try this with your friends and see what happens. So let's summarize what we have learned today. We have learned today how game theory is defined at all. We have learned the ingredients that constitute a game. We have been talking about the most famous example of a game in game theory. We have learned what dominant strategies are. We have learned what good outcomes are, Pareto, efficient outcomes are. We have learned how to find a Nash equilibrium. And we have discussed the question, are Nash equilibria unique? Then we have considered an example where Nash equilibria are not even discrete. And finally, we have found out, while it's very useful to study game theory if you ever would like to win a world championship final in soccer. Thank you very much for your attention.